Hello, and welcome to this Let's Chat Detector Building. My name is Karen Emmons, and I am a VASO board member, one of the technology event group leaders, and a national event supervisor. I'm accompanied today by Kira Emmons. Give me a second to spotlight us. Kira is a member of VASO's Appeals Committee, as well as an event group leader for the electronics and some of the inquiry events. She works professionally as an electrical engineer. She's been our mind behind Detector Building ever since the event's debut in the 2019-2020 season. A quick disclaimer before we get going. In our time this evening, we cannot possibly cover every rule or situation that might come up at a tournament. Nothing we say here today supersedes a rule or rule clarification. You still need to read the rules. Read the rules often, because every time you do, you'll see something new, and then read them again. And don't forget about the VASO clarifications on our website, which are just as binding as rules. As we talk, I encourage you to put your questions in the chat so we can incorporate them into our conversation. So I know we've got lots to talk about, so let's go ahead and get started. Kira, thank you for joining me this evening.
Happy to help.
All right, Kira, your volume's a little bit low, I feel like. So, okay. So Kira, what is the task in Detector Building?
Can you hear me better now?
Yes, thank you.
So the task essentially is to build a mass or force sensing device, in this scenario, mass enforcer equivalent, that will accurately measure and display both a voltage and the actual masses of different solid samples ranging from 30 to 1,000 grams. And teams also take a written test on the topics relevant to building that device.
Great. All right. So how is this event scored?
So your score comes in three main components from that written exam, from your device, and from a design log. And the device score is also split into two pieces. There's an accuracy score and an LED score, which we can get into a bit later. If you've read the scoring section of the rules, which of course we highly encourage you to read every section of the rules, and reading about how you get points is pretty important. It's pretty complicated though, but sort of filtered down. Well, it even depends at what level of tournament you are, but at regionals, your score is 23% design log, 36% written test, and 41% device. And the device has a higher percentage at higher levels of tournaments because there's an additional unknown test mass.
All right. As somebody who comes from the physics events, I'm impressed by what a big percentage of the total score the design log is. That's significant in terms of science Olympiad events.
It's unusual in that way, yeah.
All right. I know that we have a lot to say about the build, but why don't we just have a quick look at whatever you'd like to tell us about the written test?
Sure. So while we're on the topic of scoring, know that your exam score is scaled according to other teams' exam scores. So basically, the written test ends up being out of the highest number of points that any team at that tournament got on the test, instead of being out of the maximum number of points available on the test. So that basically just ensures that like written tests portion of your final score really does amount to the full, what did I say, 36%,
Yes.
instead of being artificially reduced because the test was just really hard or anything like that.
Nice.
And that's pretty standard for all of our hybrid events, both physics and technology. I also just want to note that the test topics align really closely to the construction of the device. Since this event is categorized as a technology event rather than a physics event, like all of the other hybrid build test events are, detector building has more of an engineering test than a physics test. So studying for the test will actually really, really help you with building your device. It's not like it's about time where you're supposed to learn about the Mayan calendar and then build a metronome. Like they're related and they're both interesting, but they're not going to help you with each other. Um, Here, they're very strongly correlated. So actually, before you start building, I know there's like a big temptation to just jump into making the device and worry about the written test later, but I really recommend you do it the other way around. You should know at least about all the electrical parts that are mentioned in the rules, the difference between analog and digital electrical signals. You should know about microcontrollers, transducers, breadboards, and the basics of like conditionals and loops in code before you ever start building your device. It's just really going to help you plan and be less frustrated when things go wrong and you have to fix them because you'll already have an understanding of what's going on.
That is tremendously good advice, because I think most teams, at least in the physics events, they start the build really early and need to, right? But I'm not sure how I feel about the dig at It's About Time, which is my event. But all right,
Yeah.
that's it's a reasonable comparison. So
Yeah, I had a computer science professor in college who used to say that software engineering is 30% writing your code and 70% debugging. And I think that, well, that has certainly turned out to be true for me. And I think it's quite true in electrical engineering as well. So don't expect to be able to just plug things in and have it all work. You know, things are going to go wrong and you're going to have to fix them. And so having a baseline of knowledge ahead of time, I think is really super important here.
great. Well, then let's get to the advice. We've got our baseline of knowledge. What are all the different pieces of this device?
Okay, I have a figure to show for this. So I'm gonna show, well, I'm gonna share my screen. So this is the VASA website. Hopefully you've seen it already. Let me actually show you how I got to this page. So going back to the home page here, we go up to middle and high school, and then select events from the drop down, and then we scroll to detector building. And so we've got this page all about detector building. Hopefully you've already taken a look at this or will now. We'll discuss some of these clarifications as we talk, but there's also some resources down here. So I'm going to open the block diagram just to answer this question. Okay, so a block diagram, if you're not familiar with it, is something that a lot of engineers really like to use. It's a very, very high level description of the relationship between different components of a system. So, so this, in a basic nutshell, is your device. At the center, you have to have a microcontroller, which is basically a really, really low power computer. Um, and often they're on circuit boards that allow you to easily have inputs and outputs to them. So you're also going to make a sensor that provides input to your microcontroller. That sensor is going to be measuring directly force, indirectly mass. And then you are going to have two types of display. You're going to have a digital display screen, which shows numbers, the raw voltage and the converted mass that you're measuring. And then you're also going to have a bank of LEDs, three of them, a red, a green, and a blue. And you will have to light them up according to what range the value is in, the mass is in, and you'll get those ranges during your setup time at the tournament. So you'll have to do just a little bit of live coding. And so in order to program your microcontroller, you can use either a laptop or your calculator if you have one of those like fancy TI graphing calculators. And then I think the easiest option is to use that same laptop or calculator as your display screen as well as the power supply to your microcontroller. But some teams opt to use a separate LCD display. That's a little extra work in my opinion, but you're welcome to if you'd like to. I think that covers most of the construction parameters in 3A. That rule is basically outlining just what pieces have to be in your device, and it also tells us that you may not at any time have a Wi-Fi or internet connection. So if you're using a laptop, you can't connect it to the internet.
Okay, great. So just as a reminder to teams, Rule 3, all the subcomponents of it tend to be about the construction of the device. So I think that that's what we're moving into now. We've seen the block diagram. What else do we need to know about the construction of the device?
So if we move on to Rule 3B, I'm going to go back to this page of our resources and open the other one. Rule 3B is mostly about telling you which components you're allowed to use in your device, like getting a little more specific than our general block diagram. So on this slide, I have things that you're allowed to use. Of course, a microcontroller and a display screen. You have to have those things. And a breadboard. Hopefully you know what that is. If you don't, you can do a little bit of reading on how to use one, but essentially it's an easy way to create some supporting circuits for your device. And you can use either a solderless breadboard, which is the most common variety, or you can use a solderable breadboard, where the pins are still laid out in the same arrangement, but you can actually physically solder your pieces to it. You're allowed fundamental electronic components like resistors, capacitors, LEDs, IC chips. All of that has to be assembled on some sort of breadboard. And you're also allowed strain gauges and force sensitive resistors, which are the two primary sensing pieces that you can use to create this force sensor. And then we have another slide with no, these things are not allowed. And the big thing that's not allowed is circuit boards, except for the few specific types that I showed on the previous slide. So you're allowed a microcontroller, that's a circuit board. You're allowed a display screen, that's a circuit board. If you use a separate one, or I mean, I guess if you're using your laptop or calculator, there's circuit boards in there. And then you're also, if you choose to use a solderable breadboard, which would not be my choice, it's hard to undo something that's soldered and change it. But if you would like to use that, that is allowed. Note that that is a very specific kind of circuit board, and it will be sold as a breadboard. So any other kind of circuit board, whether you've purchased it, whether you've had it custom made, is not allowed. We have one clarification about this. In general, our clarifications, I think, are very much in line with the national clarifications. Remember, we only use Virginia ones. National ones don't apply in Virginia tournaments. But in general, we try to keep them very closely aligned. But we do have one that is directly contrary to theirs, where they have allowed teams to mill their own circuit board. We do not allow that. It doesn't matter where it's come from, you can't use it. I can't really fathom literally milling your own, though. I don't think that's a thing most people do. That's not just like a machine you buy. That's not a normal thing. But anyways, so we've got a couple examples on this slide of circuit boards that would be disallowed. And again, all those same fundamental electronic components, resistors, capacitors, LEDs, IC chips, they are not allowed when you've assembled them on a circuit board, only when you've assembled them on a breadboard. The other two things that are disallowed are pre-assembled load cells. Whatever you end up making as your sensor can probably be described as a load cell. So you are making a load cell, but one that you buy that is already made and you just plug in, that is disallowed. You need to make it yourself. That's the point. I think we also, we have a clarification that's closely aligned with nationals that explains exactly what we think pre-assembled is. Actually, let me go find that for you. Here it is. So for the purpose of evaluating the construction parameters, a load cell is defined as a pre-assembled device where the strain gauges are already wired together or attached to a flexible material. Okay, coming back here. And the last thing that's not allowed is batteries that combine to more than 12 volts. And we judge that based on the manufacturer label. We aren't like physically taking a voltmeter to your batteries. But again, probably very few teams are actually using batteries. Most teams choose to just use the power from their laptop or their calculator. So then you wouldn't have to worry about measuring that at all.
If you're using batteries, you can set them up in either a parallel or a series arrangement, right? It just, whatever it is, it can't be more than the 12 volts.
Correct, yeah. So lastly, we have one kind of special case, which is an additional type of circuit board that is allowed. And I don't want to spend too much time on it because it's a thing you're very unlikely to encounter, but the rules do allow you to use something called a surface mount adapter board, which essentially if you get a circuit component that doesn't have pins that go down into a breadboard and instead is meant to just sit on top of a circuit board so that you can solder it, you can use this type of adapter board to put pins on it so it can go in a breadboard. I don't recommend you use this. Usually if you find a surface mount component you'd like to use, it will also be sold in a variety with the pins on it. And that's just a lot easier. But you can use one of these. It is a circuit board that has no other circuitry on it, only one element, and it just connects the surface mount pins to like vertical pins that can go into a breadboard.
Okay.
So I've been talking for a long time, but that's rule 3B.
Well, that's really important, though. These are I think that this has been was a source of some confusion about what could be used and what could not be used, and load cells and things like that. So your exhibits with some pictures and of kind of a more pulled apart version of this is really helpful.
And it's really important to get this right, because if you violate either of those two rules, your device score gets multiplied by 0.6 per violation. So another way to think about that is a 40% reduction of your device score, which is a really huge penalty, which I think is warranted.
Every time you goof too,
yeah.
Right? So if you use two wrong components, it's okay.
Yeah, so be really thoughtful, because if you violate either of those rules, you're really not doing the task, which is why the penalty is so large. There are a few more rules in that construction parameters section. If you violate them, that results in a 20% reduction of your device score per violation, which is still very large, but smaller. Rule 3C, I think, is pretty important. It has to do with sort of physically how your device is set up. It has to accommodate the masses that we give you to test with. And it's worded in a slightly odd way, unlike most of your technology events, which tell you just you have to fit this measurement, or tell you like exactly what size your device should be. Instead, it tells you that you have to accommodate a mass of a certain size, 8 centimeters in diameter. So essentially, well, I would recommend you just make a platform that is at least that large and rigid enough to hold the maximum mass, which is 1 kilogram. You also can't have any height obstructions. So that means like you can't try to hang our mass or anything like that. Basically from the surface of your device that the mass gets placed on up to the ceiling of the room, there shouldn't be any obstruction. So we're allowed to make the mass as tall as we want. Does that make sense?
I think so. So the 8 centimeters in diameter, we're not talking necessarily then about a spherical mass. You're taking the 8 centimeters
Or
in diameter to be like
a
cylindrical mass. Okay.
Yeah, but I mean, we could easily give you a cube or something that's within that size. Yeah.
Okay.
So just keep that in mind. Whatever masses you choose to test with probably won't be that big. 8 centimeters is pretty large, but keep in mind you do have to be able to accommodate something that large. Rule 3D tells you a little bit more about that digital display screen and what has to be there. You have to show both the raw voltage measurement that you get from your sensor and the mass in grams that you've converted that to. Please remember you need to put units on both of those numbers. Everything in Science Olympiad needs units. And the rules also specify that you give us the mass to the 10th of a gram. So please just do that. Don't give us more, don't give us less. Rule 3E is about the LEDs, and it's less construction parameters for you and actually more rules for us about what LED ranges we're allowed to give you. But it does tell you that you may not use combined RGB LEDs, or if you do, you can only wire them for one color at a time. And rule 3F is about powering your device. You may not use electrical outlets, so charge your laptop. And if you do choose to use commercial batteries, the total input voltage cannot exceed 12 volts, like I showed before. And if you have a higher voltage, unfortunately, we have to determine that an unsafe device to test. So we actually won't be able to test your device if you go over that. So be mindful. Okay. And I think that takes us through all of the construction parameters.
If we were to use a calculator or a laptop for powering the device, we know then that it's under 12 volts. We don't have to worry about that or figure something out about that.
Actually, the way the rule is written, I think they may be more than 12. I forget what a USB cable is, but if it's powered from a laptop or calculator, we don't care. The rules tell us not to
worry
make
about
any measurement. Yeah. It's
Okay.
only if you use batteries that we're going to count.
All right. Just checking to make sure.
Oh, we
that...
have a comment that says USB is 5 volts. So yes, it's under 12.
Okay, great. Great. All right, well, that's a lot of pieces to pay attention to be careful about, and clearly, given the heavy dutiness of the penalty, important to pay attention to all those pieces. So assuming we've done all the things right,
Yeah.
how are you gonna, you said that there were 2 pieces to the device score?
Right. So the LED score is the simpler one. Basically, for each of the test masses, there's 3 at regionals, 4 at states. You get 4 points for each of those. We can call them like stations if you light up the correct LEDs, and 0 points if you don't. And we judge that based off of we judge whether it's in the correct range for the LEDs based off of the mass that your device displays, not based off of the true mass, because we don't want to like ding you twice for getting it wrong. The
Okay,
accuracy.
so just to make sure I really understand it. So if the mass weighs a kilogram and I say it weighs 30 grams, and light up the wrong LED color because my mass said 30 grams, you're gonna give it to me if
we're gonna judge if you lit up the right color based on that 30-gram measurement, not based on the true value of a kilogram.
So you're not going to say, well, I'm expecting you to light up the blue. You're going to give me ranges, and from here to here it's green, and from here to here it's blue, and that kind of thing. Okay, great.
It states those ranges are allowed to overlap, so we could ask you to have more than one on at a time.
Oh, okay.
So it gets a little more complicated, but I think we can talk about those tips more in a later section. The other piece of your device score is the accuracy score. Formula is a little complicated. We use like the relative error, like the true value minus your measurement over the true value, and then there's a multiplier that depends on the level of tournament, and then it's 15 minus all of that, so like it's a maximum of 15 per station, and we never go under 0. You're not going to get negative points, but essentially know that it's relative error, and that the higher the level of tournament, the closer you're going to have to be to the true value to get points from it. At regionals, the minimum mass is 30 grams, right? So you stop getting points once you are 22.5 grams off, if that were the true value, and then if the true value were at the upper end, 1 kilogram, you would stop getting points once you're 750 grams off at regionals, and it sort of scales between those two, just depending on how large the true mass is.
So you have some real leeway here.
Yeah, it's actually a pretty wide window compared to like trajectory.
Right.
I'm just taking shots at all the other events.
Yeah. Pun intended.
Yes.
All right. All right.
But also know that you can download the spreadsheet that we use to score. I don't think we have our VASO versions up quite yet. They should be up once we get a little closer to regionals, but you can get the versions off of the national website already, and they're very similar to what we end up using. So you can like practice typing in the numbers from your tests and see what score comes out of it, because doing this math by hand is kind of a nightmare.
That's a good tip. Look, the VASO version the links for that will appear on the event page. So, and we hope to have those up in a few weeks. So where do you start? This is a lot. If you're new to this whole event, where do you start?
Yeah. Well, like I said before, start by learning a little bit. Make sure you know enough to understand what's in the rules, at a minimum. Once you do, a really big piece of advice that I have that every engineer learns the hard way as they're going through school is build modularly. So there's a lot of components to this device that all have to talk to each other. There's lots of inputs and outputs, and you're gonna have code running. So when something goes wrong, it's really hard to assign that to a specific piece and figure out what the problem actually is, because they all interact, and maybe there's problems with multiple pieces and those problems interact and create a new problem, and you can't figure out what's going on. So the key here is build and test one component at a time. Test it really thoroughly. Make sure you know ahead of time what you expect its behavior to be, and then test for that behavior. And then you know that when you're adding on new pieces, if there's a problem, it's coming from whatever that most recent addition was. So we say build modularly as if each of these is a module that you add together. And that's going to make your life so much easier. I've talked to some students at tournaments that just didn't start early enough to really learn much about the components in this event, and so they just found a tutorial online that seemed vaguely similar to the device we're asking you to build, and they just tried to build that. They plugged it all in and it didn't work, and then they didn't know what to do about it, or they got a little bit of output or like sporadic output, but they didn't know what was up, and it was really frustrating, and they just wanted to quit. And I don't want that to happen to anybody. So build it up gradually in pieces. Don't expect to be able to build anything without understanding how it works, because it won't work.
Okay.
So just connect your microcontroller to your display, and just like write a very simple program that prints numbers in a loop, and just like make sure you can talk between your microcontroller and your display. And then for future steps, you always know that you can add print statements to your code to help you debug, because then like you already know how to do that, so you can see if the code is getting to that point, or you can print a specific value to your display to help you debug. Then go add your sensor, plug it into your microcontroller, have it print the raw sensor reading in that loop, and then just verify that those readings are what you expect, and make sure that they actually vary with the force applied to your sensor. Apply more or less force, and see that they change. Like then you can move on to gathering calibration data and use it to derive an equation, and then factor that into your code and print the mass value then that you've converted to. Then you can work on adding your LEDs. And of course, finally, once you get to the end, I strongly encourage you to just reread the rules, verify that your device meets the requirements, and maybe have your coach help you do that, because sometimes we can be blind to certain things when we've built it and you're attached to your device. So just getting an outside set of eyes can be helpful.
That's a great set of order of how to break down and where to start and step-by-step thinking, and not building modularly. I can't say that word, I think, in modules is obviously like the first place that people go wrong. But I suspect that there's some other kinds of ways people go wrong in this process. So what are some of those?
So I guess my first tip is pick a good microcontroller for you, since that's sort of the center of your device. There's a whole bunch of them on the market. The rules list a few kinds, and you're welcome to choose whatever you would like. My personal recommendation is that you use an Arduino. I think that they are very well documented online, which means it's really easy to Google what functionality they have. Their code libraries are very well documented, so you can Google how to use them. And they're just pretty ubiquitous. So there's lots of online tutorials that use them. I think you're unlikely to find a tutorial specifically for this task, but you can find tutorials for components of it or related things to give you a little bit of inspiration.
Or the modules.
Yes. Uh, and and I just find Arduinos to be pretty accessible for beginners, but also relatively powerful for experts. Like I use them for personal projects too.
I believe that there's even an Arduino kind of starter kit that has a little manual of little projects to help you get acquainted with how to use an Arduino.
Yeah, and it comes with a variety of like extra little circuit components that would be useful for your device and can just be like a useful kit for your team to invest in, I think. Um, there are other microcontrollers that we see a lot at tournament. We usually see a few teams using a Raspberry Pi. I think often because they want to write in Python. You can write in any language you want on a Raspberry Pi because it actually runs a full Linux operating system. So I don't recommend it for beginners. It's significantly more complicated than using an Arduino, but they're certainly a great option for anyone who wants to use that. The last one that we see pretty frequently is the TI Innovator, which is the one that is meant to plug into your TI graphing calculator. It's not at all documented online. They do have some tutorials, but writing code on your calculator is awkward, and it's not really like any coding language you would like really use. So if you want to use this event to get into coding for the first time, um, like learn to write a real coding language like C++ or Python or not what your calculator uses. But
I
we
would,
do see teams use it and we've seen them be successful. So you certainly can, but it's not what I would choose.
I think also many people just own the TI thing. They have
That's true.
access to the TI suite. So you're not, it may not always be the easiest or the most straightforward, but if you have it and and your school has those resources, you're not going to be at a disadvantage. Right.
Yeah,
It might just be, so it doesn't put you at a disadvantage to use it. It just might be a little trickier to get into it if you're new to coding or whatever. You'll have to learn a kind of a different set of things around coding.
sure.
What other ways do people go wrong?
Um, I think people forget that there's a mechanical component to constructing electronics. Um, I sometimes hear from students at tournaments that they have pieces like coming out of their breadboard and then they try to put them back in, but sometimes they like put them in the wrong spot or they just don't notice something's come out and it causes them problems. And I think this happens particularly with like weightier components, particularly if you're using like a separate LCD screen. Those can pop out of your breadboard pretty easily. So just be like mindful about supporting that weight. One thing that's pretty common is people will put their, oh gosh, people will attach their microcontroller and their breadboard to like a backing board so that they're already kind of connected, and that makes it easier to put wires between them and you don't have to worry about stuff pulling on the wires. Um, Also think about like spacing things apart on your breadboard because you don't want wires to touch that aren't supposed to. And particularly when people have like, I don't know, LEDs or resistors on like really long wires sticking up from their breadboard, especially in like transit, get smushed around and end up touching and causing electrical shorts, which can blow out some of your electronics. So one thing you can do to help that is to like space them apart, or just like cut those wires shorter. That's what I usually do. If you have wires like coming off of your breadboard, maybe like to your sensor, which is not going to be physically, it'll be electrically connected to your breadboard likely, but not like physically attached. If you've got any exposed joints, like cover them with electrical tape. Another thing, oftentimes electrical components can come in like ribbons like this, or sometimes they look like this, and there's like a tape down here that's holding them on. Don't just pull these out, because then you've got that like sticky stuff on the wires and that can cause you problems. Just take some wire cutters and cut these off. Like there's plenty of length up here. That's what you're supposed to do. Or just like cut them off on the sides here. Don't just pull them out. Do I have any other mechanical advice? I also just like to have a pair of like pliers next to me, because like wires get bent or can get like stuck in your breadboard, especially if they're like small. So it just keeps things neater. I think it's really helpful to have some pliers with you as you're just assembling it all.
Okay, all right. What about the coding? Any tips around the coding?
Returning to the LEDs, I was saying earlier, at states we're allowed to make the ranges a bit trickier so they can overlap, and we can make you have more than one LED on at a time. But even at regionals, the ranges can be discontiguous. So like we could have red be 30 to 50 and 500 to 600. They don't have to come in just the 3 blocks. And we see teams be surprised by this. Well, actually, at states last year, I think teams may have forgotten that part of the event got a little more complicated at the next level of tournament. And I believe we only had one team that got all the LED points at states, which really surprised me, because generally most people would think of this as like the simplest part of the event. So I guess the lesson is don't overlook it. I think the reason a lot of teams messed it up is because they had these really large if else blocks, and they were trying to sort of manually separate the ranges and say, like, if you're in this small range, it's these two, and if you're in this range, it's these two, or these 3, or none of them. Instead of doing that, because you only have a 5-minute setup time to do that, just use 3 if statements that are separate, one for each of your LEDs, and just say if it's in this range or this range or this range, the green one's on, and if it's in this range, the red one's on. And that could activate more than one, or just one, or it depends on the ranges you put in, and that'll be way simpler and way faster.
That's a good tip too. What about, I'm being aware that this is an electrical, event with electricity. Are there some safety notes that you'd like to call out too?
Yes. There aren't any like circuits in this device that are really going to have enough power to like pose an excessive safety risk, very much by design. Like we don't want to put a task in front of you that could be dangerous, but any circuit can be dangerous if you don't just use your common sense electrical safety. So I think a good rule of thumb is if you wouldn't do it in front of your coach, or you wouldn't do it in front of the judge at the tournament, probably shouldn't do it. Don't plug anything in if there's like water around, you want to like protect your laptop or your calculator, or like put that lid on your water bottle. Don't lick batteries.
There's got to be a story here, but we need to keep moving on. So
it's happened to the tournament. I've seen it. Don't do it, please.
okay.
You're smarter than that. If you choose to solder anything, which you definitely don't have to make one of these devices, but some teams choose to, like, please use proper ventilation, protect your table surface. You know, soldering isn't typically considered very dangerous, but it can be if you don't just have a good setup. Another note about soldering, I've seen some teams that want to solder, but like don't have a soldering iron or don't know how to use it, and so they opt to use hot glue as a substitute. I really don't recommend that. I get that it seems like it would do that job, like you twist your wires together and then you cover it in a bead of hot glue. But hot glue is actually like very elastic, and it won't hold anything together. So those wires will wiggle around and wiggle free inside that bead of hot glue, but then you won't be able to twist them back together because they're encased in the glue. So you're just going to do yourself a disservice. Hot glue really is not a good option. Just give them like a good twist together with pliers and cover it in electrical tape, and you'll probably be good.
Okay. All right. Those are yeah, don't lick batteries. All right, there's the pro tip for the day.
Please, it's not a good idea.
All right. I know that you have a set of even more advanced ideas for teams, for teams that aren't beginners, or once you've gotten a little ways into this and you're a little bit more comfortable with all of the materials. What else would you like to share with us on that?
Yeah, if you're looking for some ways to improve your device once you've got something running, and you find you've got some more time, well, certainly I think the best thing you can do in really any Science Olympiad building event is practice testing your device the way that we're going to test it at tournament. Practice going through that procedure, and your coach can be a great resource for that. You can have your coach create some test masses for you so that you know what it's like doing that testing when you don't already know what the true masses are. And once you do that test, record the output of your device as a baseline so that you can compare the performance as you try to make other improvements. You might find that changes you make actually don't help, but it's important to have measurements of that. I think one simple thing you can do to improve your device is, since the rules tell you that we're only going to test your device in the range of 30 to 1,000 grams, consider adding just a couple extra lines of code that will keep your device's output within that range, even if your equation computes a lower or a higher value, right? Like if you get a value that's above 1,000, just output 1,000, because you're guaranteed that that's going to be closer to the true value. Also, something that a lot of teams do, consider adding a way for your code to factor in more than one measurement at a time, right? Like more data points usually leads to better results. So something like a rolling average, and you can experiment with how many data points is helpful. But often that can lead to more accurate results. Something else you can do is consider adding an external analog to digital converter, or ADC, that has more bits than the one that's already in your microcontroller. Generally, most of these like plug and play microcontrollers are going to have like a lower resolution ADC that actually limits the precision of your measurement. And I recommend doing the calculation to see by how much. and that would be a good exercise to prepare for the written exam also. But if you wanted to, you could use you could buy an external ADC in like an IC chip and put it on your breadboard and use that instead.
And that's considered an allowed fundamental
right.
electrical.
IC chips are allowed as long as you put them in your breadboard and they're not coming on a circuit board.
Okay.
And of course, I mean, if you're finding that you're having a lot of trouble with just the accuracy that you get out of your sensor, you've got a few different options for the components that you can use there. You know, I think force sensitive resistors are almost certainly the simplest thing to go with. You can just plug it into a voltage divider, but they're not the most accurate. So if you've got time, you could upgrade to strain gauges. You can read about how those are often used in Wheatstone bridges, and try some different like elastic components to attach them to support the device. And just remember that any changes you make using like any of these ideas or any ideas you have will require you to recalibrate your device. So you're going to need to take another set of calibration data and probably
Make a new
compute the new
equation.
equation.
Yeah. Okay.
One good thing about this event is taking calibration data is pretty fast if you already have a set of test masses, right? It should only take you a few seconds to get a data point versus, I don't know, it's about time, you know, it might take 90 seconds to do a trial.
Yeah. Okay.
So.
All right. Now that this is good. So we've had a question that's come to VASO about that's kind of at an advanced level. So would you address this question now?
Yeah, so we got a question from a student several months ago, and we answered that student directly. We didn't want to make them wait for this session, but in the spirit of just always offering our advice to everyone to hear, we just wanted to read that question and the answer we provided the student. So the question is, the rules say that the device should make use of a microcontroller and that a printout of the program should be attached in the design log. I particularly enjoy analog electronics and generally building things in hardware whenever possible, and would like the additional challenge of implementing my entire circuit in hardware using analog ICs such as op amps and comparators for the signal processing and A to D conversion side and discrete logic ICs for the 7-segment LED display drive and system control side of things. May I provide full schematics, block diagrams, pseudocode, and explanations as allowable alternatives to a microcontroller in section 3A of the rules, and highlighted code in sections 4B6 and 4B7 of the rules. Or absolutely must a microcontroller and software be used to fill these requirements? So our answer was, of course, we're very excited to hear that you have this interest, and we're impressed that a high schooler would have the knowledge to do what the student is proposing. However, we feel the intention of the event is to write at least a little bit of code to run on a microcontroller. There certainly is plenty of design space for auxiliary circuits as part of your sensor, but we expect to see true code in the design log for 4B6 and 7. That code can be in any language, including assembly code, which might be more in line with your interest. Implementing the entire device and hardware would be a fun extension project, though, and if you take it on, we'd love to hear about it. So I'm just going to leave that there.
Okay, so a little bit outside the scope, but an exciting question. But
Yep.
that does actually lead me to say, do you have a few words? And we're starting to run a little tight on time, but do you have a few words to say about the design log? His question had to do with what's in the design log, and it's almost a quarter of the score. So what would you like to tell us
Yeah,
about the design log?
the design log in this event is a much larger portion of your score because it's just a larger design log than most events have. And I promise that we actually take real time to score your logs. Um, and you know, we don't just look at it for 10 seconds and assign a few points and never think about it again. Like, we really consider what you've written about your device. Uh, so that means that we can also tell when you have taken the time to create them thoughtfully, or we can tell when you haven't. So don't throw away those points if it's almost a quarter of your score. Um, one side note, we haven't had a lot of issues with people forgetting this in past years, but do remember that the rules require your log to be electronically created and then printed out. It should not be in any portion handwritten. Um, an extension of that, if you only have a black and white printer, that's totally fine. Just create your log accordingly. Like, sometimes we get teams that have graphs with different colored data series, but then they print it in black and white and we can't tell them apart. Or they'll use a few different colors to highlight their code. But then when you print that in black and white, the contrast is very low and we struggle to read the code. So just like keep that in mind as you're creating it. I don't have a lot of super specific tips because I don't think creating the design log is like a super challenging thing or a thing that's going to be unknown to you. Just read the sections that the rules outlines, and once you've built your device, you'll have all that information to give us. I would just recommend giving your log to your coach to proofread, or some other teacher or a parent. Uh, the most common things teams lose points on are the sort of like back to basics of science type things, like labeling your graph well. So the person you give to proofread doesn't need to have any like specific knowledge of the event to be helpful for you on that. Just if they understand the sections you've laid out and the words make sense, like, I think they'll have good feedback for you around that.
One of the things that I know that is looked at in the log and is a huge emphasis with VASO is that students do their own work, and that the logs and the information that we see is a part of our actually evaluating this. So would you like to address what it means to VASO in this event to do your own work?
Yeah, thanks for raising that. I know the phrase like "do your own work" is like kind of an annoying cliche for most students, I think, by the time they're in high school. I think when I was a high schooler, I was annoyed when people had this chat with me. I was like, I know I'm going to do my own work. Of course I will. But we've actually been really surprised by how many teams haven't met our standard for doing their own work, specifically in this event. So entertain this reminder for a moment, please. Um, I will also say I highly recommend just reading VASO's constructed devices policy on our website. It'll only take you like literally 1 minute to read it. But that is the full text of what we expect. But what I want to highlight here in particular is that we consider writing code part of constructing your device. So your code and your design log, like Karen said, must be your own work. We've seen cases where teams have given their code file and their design log to the other teams at their school to use. We've seen cases where a team downloads a file from the internet, or even we've seen them get it from competitors in other states. I guess they've met online somehow. we take this very seriously, and if you are outright using someone else's work, it's cheating, and our penalty for that is disqualification. If you make very significant modifications to work you get elsewhere, we will consider it yours. But things like just going through and changing the variable names, or just like adding comments, or like slightly rewording the design log, are not significant modifications. We want to come away looking at your device and reading your design log with a strong feeling that this is your own work that you've presented to us. And in order to help us judge that, we do have a clarification. I'm going to share my screen again. 1 second.
While you're doing that, while you're getting ready to do that, I'm gonna add a little bit and say that in this event, we have people who are skilled and knowledgeable look at this stuff. And these people also do know that, most people often don't start entirely from scratch when they write a program. That we are dependent on things we see other places. We use a little bit here, we might use a little bit here to give us some, and we're knowledgeable about that. But it is the straight just taking of somebody else's code for this event.
Just
and we
sort
can
of
recognize
wholesale copying. That's what we have an issue with. If you copy a couple lines of code from a tutorial online, that's perfectly normal.
And we get that. So I did
Yeah.
want to say that we understand that line, and and these are people that do their own programming, so they know that they walk that line themselves. So anyway,
Yeah,
you're going to show us the clarification, Kira.
Thanks for adding that. Okay, so this is the clarification. It says VASO considers writing code to be an integral part of building a device. So the constructed devices policy applies to the code as well as to the physical device. And this is a link here, so you can click to read that policy. To ensure the policy is being followed, teams will be required to transfer a copy of their source code file after they have modified it during the setup period onto a USB flash drive provided by the event supervisor. The team is responsible for ensuring they will have a way to connect the provided USB flash drive to their laptop or calculator. So we are going to do our best to judge your device during the time where you're competing, and we'll talk to you about all of this. And but we do want a copy of your code just to have if we need to take a look back at it later. So to that end, like the clarification says, we will provide you with a flash drive and expect you to copy your code onto the flash drive. If you're using a laptop that has your standard like USB port, great. If your laptop doesn't, maybe you're using like a Mac and you have USB-C or a Lightning connector or whatever version Apple is on now, please bring an adapter so that you can plug that in. If you're on a calculator, things are a little bit more complicated. Just search up TI's recommendations for whatever model you're using, and you're probably also going to have to bring a laptop as an intermediary for that transition. So just make sure you have a plan ahead of time for how to give us the code.
And it has to be the modified code because we want to see how you've modified it based on in that 5 minutes at a time.
That's a big tell for us if you know how to make the change that's expected during the setup period. We believe that you know how to write code and can modify it. But if a team hasn't made those modifications, it can be a flag for us to just look a little closer.
All right. That was a difficult topic, but an important one because we have encountered this and it's a struggle and it's discouraging. Let's move on to what does this event look like on tournament day?
Right. So in Virginia, for our regional tournaments, we have written tests separated onto a different day from device testing. So at our tournaments, you're going to see those entirely separately. If you go to other tournaments, you might see them happen together where you sit down for the written test and sort of get pulled out for a few minutes to do your device testing. But essentially, you'll be given your 5-minute setup time during which you have to adjust your code for the LED ranges that you're given. Also, if you bring your own calibration masses, we will give you our scale to use during that time as well for your calibration, but you're not required to do that. And once your setup time is over, you can't modify your device anymore. So we'll do a quick construction check, make sure everything checks out, and then you're going to go through each of those 3 stations for regionals or 4 for states. You get 60 seconds with each, and you'll just be provided the unknown masses to place on the scale that you've constructed, and we'll take the reading off of what your device outputs.
Now, yeah, let's talk about that device output though, because isn't it maybe sometimes a changing thing, or what happens with
yeah,
this?
so some people set up their devices to output a data point every second, or sometimes even faster than every second. Sometimes people have it much slower and they'll do every like 5 or 10 seconds. Any of those can be good strategies, but whatever you choose, we'd appreciate it if you sort of kept in mind our ability to read what's coming off of your device, because if it changes very quickly or like is scrolling on your screen really fast, we might not actually be able to like read the whole data point to write it down. So one thing that can be helpful is if you have a way to like pause your device. If you're using an Arduino and just printing to the serial port, there's actually already a pause button built in. But if you have if you have a different setup, we'd just appreciate it if you could have like a key that you push that pauses it briefly, just so we can like write it down. Because otherwise, if we can't read it, we might not be able to write down accurately what your device outputs.
Okay.
But once we and also remember that we're writing down the voltage and the mass and the LEDs, so it's a lot for us to try to capture in that one moment if it's going by really fast. But once we've finished those 3 or 4 stations, we'll just have you put your modified code on our flash drive, and then you're done.
Are there some common, so the bit about the pause button, I feel like maybe we should have even discussed that in the construction, because it's just such a useful thing. But
it's not a thing that's useful for you maybe, but it's really useful for us. And if I mean, if your output scrolls, you know, if you're outputting at like 50 hertz or something, then like we may not actually be able to test your device if we can't read it. So just be thoughtful of that.
Any other common problems on tournament day?
Like I said before, I think it's really important to practice using your device under the tournament conditions. Like the rule, I mean, I've just given a sort of brief overview of what our test procedure is, but the rules given in a lot of detail. So practice under those conditions, practice where you don't know what the correct value is. I find that can really affect how a team performs. And I guess my other advice is don't ignore significant figures and units either on your device output or on your written test answers, because that can be a really easy way to have a lot of points taken off.
That's right. Units also on the device in addition to
Yeah.
your exam. Another good pro tip, because I know we've seen a lot of instances where teams haven't done that.
Yeah.
I'm looking to see if we have any questions. It doesn't look like we do. Kira, do you have any final pro tips for us or anything else you'd like to add here at the end?
Gosh, I think that mostly covers it.
It's a
I feel
lot.
like I've
There's
said
a
a
lot
lot.
to think about. We'll put chapters in this YouTube video so people can scroll around where they need to. That was a lot of good information. I feel like I know a little bit more about how engineers approach their work. And we're excited to see everybody at tournament. We hope you enjoy this event as much as we do. Again, Kira, thank you very much for your time this evening.
Of course.